Hello, welcome to lecture 14 of the course. In the last couple of lectures, we have learned about the density matrix formalism and some of its applications. In this lecture, we'll see how density matrix formalism can be used to deal with the so-called open quantum system. In this regard, we are going to derive a quantum master equation, also known as the Lindblad master equation. And I'm going to derive it in great details. The derivation is quite involved, but you must know the derivation. However, this lecture is not going to be part of the examination. So let's begin. Let us begin by asking this question: what do you understand by an open quantum system? An open quantum system is the one that is coupled to external system that we do not directly track. Now here in this diagram you see the system is there and it is surrounded by the environment. That means the system is interacting with the environment. This environment is also sometimes termed as reservoir in the quantum optics language, and mostly the term reservoir is used. And in fact I am going to represent reservoir by the symbol capital R and the system by the symbol capital S, and the total system consists of the environment and the system. That means the reservoir plus the system. And we are going to assume that the system and the reservoir is interacting very weakly, or the coupling between the system and the reservoir is weak. So this is what one major approximation that we are going to use to derive an equation for the system evolution. So I will come to that later. So first assumption that we are going to make is that the coupling between the system, let me say system S and reservoir R is weak. Alright. Now the system is represented by the Hamiltonian Hs, and the reservoir is described by the Hamiltonian Hr, and the interaction between the system and the reservoir is described by the Hamiltonian Hhr, right? And the total Hamiltonian in that case is going to be system Hamiltonian plus the reservoir Hamiltonian plus the interaction Hamiltonian between the system and the reservoir. Now the total system evolves unitarily, and this evolution equation for the total system is given by this density matrix equation, the so-called von Neumann equation. So delta rho SR delta T is equal to minus I by h bar. H bar is the reduced Planck's constant, h rho SR, and here rho SR, that is the density matrix. This is the density matrix representing or describing the composite system or the combined system, describing the combined state of the system and the reservoir. However, we are interested in deriving an equation for the evolution of the system only, and our objective or the goal is to derive an equation of motion for the state of the system alone. And as we have already learned about the reduced density matrix, so you can clearly see that to get the density matrix of the system, we need to trace out the reservoir, and we can do that by taking the trace over the reservoir, and this is what we are going to do. And here this rho is what I am going to use to describe the density matrix of the system. Now in order to derive a master equation describing the time evolution of the system state, it is better to work in the so-called interaction picture. I am sure you are aware of various pictures or representation of quantum mechanics. Still, let me briefly digress and offer you a discussion. So I am going to discuss about various pictures or representations of quantum mechanics.
representations of quantum mechanics. Here my discussion will be brief, and I request you to consult any standard quantum mechanics text for details. So as you know that there are three representations of quantum mechanics. One is the so-called Schrodinger picture, who is all of you are familiar with, and another one is the so-called Heisenberg picture, or representation, and finally the so-called interaction picture, which is of importance for us for this particular course and in particular for this lecture. So in Schrodinger representation, the state vector of the system is time dependent. So the state is time dependent and the operator is time independent. As you know, the operator represents any corresponds to any physically observable quantity, so it is time independent. So let me put a suffix s to represent the Schrodinger picture. Let me briefly talk about the Schrodinger picture first. In the Schrodinger picture or the representation, the state vector evolves with time according to this equation, which is basically nothing but the Schrodinger equation, which all of you are aware of. And this equation can be written, if we solve it, we can get a simple solution. I can write it in this form: psi of t is equal to e to the power minus I by h cross h of t psi of 0. And this particular operator is the so-called evolution operator, and it is generally represented by the symbol u, t0, psi of 0. Okay, so this is how a state vector evolves in time as per the Schrodinger representation. And the operator, if we have to find out the expectation value would become time dependent, though the operator is time independent in the Schrodinger representation. So expectation value is calculated by this formula, where psi of t is the normalized state vector, and as, let me put it, that this represent the operator in the Schrodinger representation. Alright, so let me write it as equation number 1. Now there is an alternate picture, that is the so-called Heisenberg picture. In the Heisenberg representation or the Heisenberg picture, the operator is now time dependent, and in that case the expectation value of the operator is worked out by this formula, and the state vector is now time independent. It does not depend on time. Operator evolves in time, and you have this equation as your expectation value equation. So you just look at equation number 1, and let me say this is equation number 2, and let me put the symbol as h as a suffix to represent the fact that we are discussing Heisenberg picture. And now in this case, the operator evolves in time. So in Heisenberg representation, you have an evolution equation for the operator, and this equation is the so-called Heisenberg equation. So let me put the symbol h here again. So we have this as our equation, evolution equation for the operator. And the time evolution and the state vector does not evolve in time, so the state vector is static, so it is simply psi of 0. And as you know that this is actually the time evolution, the state vector in the Schrodinger picture, and this I can write at time t is equal to 0. So it will remain as it is in the Heisenberg picture. What the Schrodinger picture, the state vector at time t is equal to 0. So I can also write it by this equation: u dagger t of 0 psi of t in the Schrodinger's picture. Okay, so from here I can also work out the density matrix for the state vector in the Heisenberg representation. So this is basically the usual way you are going to calculate it. So get psi h, bra psi h, and if you put this expression from here, psi of h is equal to this one, if you use, then you are going to get rho h is equal to u dagger t0, you will get rho s of t. It's very easy to see, please do that, u of t0. So this is the density matrix in the Heisenberg picture. Okay, and now coming to the interaction picture, which is of our interest. In the interaction picture, it is basically, is a hybrid of the Schrodinger and the Heisenberg picture. And here in the interaction picture, the Hamiltonian S is decomposed as H0 plus V, where H0 is the Hamiltonian representing the system without any interaction, and V is the interaction part of the Hamiltonian. And then in the interaction picture, actually is essentially the Schrodinger picture with respect to the interaction Hamiltonian V, and but the Heisenberg picture with respect to H0. Alright, now here the state vector in the Schrodinger, in the interaction picture, it is related to the Schrodinger state vector by this expression. This is e to the power I by s cross h0 of t. So this is how the interaction state vector in the interaction picture is, and from here you can work out the density operator in the interaction picture. That would be skate psi I bra psi I, and if you work it out, then you are going to get rho I is equal to e to the power I by s cross h0 t, rho s, that is the density matrix in the Schrodinger picture, e to the power minus I s cross h0 t. And you can actually work out the evolution equation for the state vector, and that would be simply given by this equation. And here you see it evolves, the state vector evolves because of the interaction Hamiltonian, interaction part of the Hamiltonian, and the density operator also now evolves in time in the interaction picture. Del rho I del t is equal to minus I by s cross the commutation V rho I. Okay, so this is in nutshell. You have what about the interaction picture. By the way, the operator also evolves in time, and the evolution equation for the operator in the interaction picture is this: del ai del t is equal to minus I by h cross ai h0. I think we are going to solve some problems in the problem solving session number 5 involving this interaction picture and other pictures of or representation of quantum mechanics. Some of these expressions that I am writing here, maybe we'll derive it there as well. And for now, we are going to utilize these results or the expressions that I have written here. In particular, please note this particular expression for the density operator in the interaction picture, as well as you just keep in mind about how density operator in the interaction picture, how it evolves in time. So this equation is of importance for us, as well as this equation. As we are now aware of the interaction picture, let us write the combined state of the system plus reservoir, which is rho SR, the density matrix for the combined system and reservoir in the Schrodinger picture. Let us write it in the interaction picture. In interaction picture, we'll denote it by this symbol with a tilde sign above it. So in the interaction picture, this is the density matrix for the combined system and the reservoir, and the interaction Hamiltonian, corresponding interaction Hamiltonian in the interaction picture is going to be this. Just again, once again, you please recall that in the interaction picture, the density matrix is written in this form: e to the power I by h cross, which already you have written, but I am writing it again so that you can compare it. So this is what I have. Here you see h naught is the Hamiltonian corresponding to the isolated system without interaction. So here H0 consists of two parts. One is due to the system and other is due to the reservoir. Similarly, for the operator, as we have already written in the interaction picture, operator is written in this form: e to the power I by h bar h0 t and this operator in the Schrodinger picture is as e to the power minus I by h cross h0 t. Okay, so if you now just look at this expression and just this expression, so things should be clear to you. Now the equation of motion is now going to become, in the interaction picture, delta of rho tilde SRT del t is equal to minus I by h cross h tilde SR of t rho tilde SR of t. And in fact we have already written down the evolution equation for the density matrix in the interaction picture. So let me again show you here. So as you can see, this is the equations as I have said. Please, that this equation you should note it down. And here V is the interaction Hamiltonian, and for our case the interaction Hamiltonian for the system reservoir is this one. So this is going to be our key equation, and this is basically the basis of our derivations that we are going to do now. So let me name it as equation number, let's say, I think we have already noted down some equation number. So this was equation number 2. So let me now name it as equation number 3. Okay. Now let us integrate this equation number 3 from time t to t plus delta t on both sides. And you can see that on the left hand side of the equation you are going to get this expression, and on the right hand side I'm keeping it as it is. Then from this equation number 4 I can get an expression for rho tilde SR at time t plus delta t, and inserting, actually we can now iterate this equation number 5, actually equation number 4, by using this expression for rho tilde SR at time t plus delta t. So this expression we can utilize in this expression for equation number 4 for rho tilde SRT dash. And if I utilize it there, then you will see if you just look at equation number 4 once again, here as you can see the left hand side of the equation remain as it is. I just have put the expression for rho tilde SRT dash utilizing equation number 5 here, and this is what I have put. And then I am going to get on the right hand side of this equation these two terms we are going to get. So this is the key expression finally we obtained for rho tilde SR at time t plus delta t minus rho tilde SR at time t, and this is what we are going to get. But this is the density matrix. Difference of the density matrix for the system reservoir, combined state of the system and the reservoir at time t plus delta t and time t in the interaction picture. But we are interested in the density matrix for the system only, so we have to trace out the reservoir, and to do that we have to take the trace over the reservoir on both sides of this equation number 6. However, before we do that, we are going to make an assumption that trace over the reservoir, this commutation, this expression h tilde SR t dash, which is here I am talking about this commutation relation. If you open up this commutation relation, you will have a product of h tilde SR rho tilde SR at time t, and this what we are going to assume that this is going to be equal to 0. The reason behind this assumption is as follows. First of all, as we have already know, and already actually I told you that the coupling, because of the fact that the coupling between the reservoir or the system and the reservoir is weak. System and reservoir is weak, and this is because of the fact that the reservoir is a very large and complex system, and also because of the coupling or the interaction between the system and the reservoir is weak, we can always take this combined state of the system and the reservoir to be factorizable. So I can write it as rho t direct product or the tensor product rho tilde r, and here rho tilde is the refer to the system state and rho tilde r refers to the reservoir. As you see, the system evolves in time, but the reservoir is behaving like a static system. Okay, and also because of the fact that this time delta t, which is much larger compared to the correlation time between the system and the reservoir. So here tau c is the correlation time. It is the correlation time between the system and the reservoir. And as you can see, the correlation between the system and the reservoir happens only for a very small amount of time, and that's the reason I can utilize this assumption. And in fact, this basically means that we are smoothing out the fast dynamics on the time scale of tau c or even smaller. So therefore we write trace over the reservoir s tilde sr t dash rho tilde srt. This I can write as trace over r h tilde srt, and here rho tilde sr is rho tilde t tensor product rho tilde r, and this is going to give me rho tilde after tracing over the reservoir only. So I have trace over r h tilde sr t rho tilde r. Okay, so this is the reason, as you can see, this is going to be equal to 0 because the reservoir state is not evolving in time. So therefore you are going to basically get it to be 0 when you are going to take the trace over the reservoir. Now because of this assumption, taking trace over the reservoir or tracing out the reservoir, we can then obtain from this equation number 6, I can now write rho tilde t plus delta t. As you can see, now I am writing rho tilde, which is the density matrix for the system, rho tilde at t plus delta t minus rho tilde at time t is equal to, the right hand side would be 1 by s bar square from time t to t plus delta t dt dash integration from time t to t dash dt double dash. Now I have trace over the reservoir s tilde sr t dash, then this term I have is s tilde sr at t double prime and rho tilde sr at time t double prime. Okay, this is what I am going to have. So just please again have a look at this equation number 6. So we are dealing with this particular term now because this term is going to be 0. Okay, so therefore this is what I get. In fact, I can now write a short notation for this difference of the system state at time t plus delta t and t. So let me denote it as delta rho tilde at time t is equal to rho tilde t plus delta t minus rho tilde t, and if I utilize it, then I can rewrite the above equation in this form: delta rho tilde t is equal to 1 by h bar square integration from t to t plus delta t dt dash integration from time t to t dash dt double prime trace over r reservoir h tilde sr t dash and the commutation h tilde sr t double prime rho tilde sr t double prime. Okay, so this is the expression I have. So this is going to be our key expression. So we are going to utilize it, but before I do that, let me make
Another assumption, this is called the Born Markov assumption, that is rho tilde SR T double prime. So as you can see, this term is here, is equal to rho tilde at time t direct product with rho r. This is similar assumption that we have already made here, as you see. Now only difference here, as you can see, that now rather than writing it as t double dash, we are writing it at time t. So basically the assumption here we are making is that rho tilde at t double dash is equal to rho tilde at time t. What does it mean? It basically means that evolution of the system state, that is rho tilde, does not depend on past history of the density operator. Okay, and moreover, let me emphasize once again that this factorization is possible because the reservoir is quite large compared to the system. Okay, and this is also the reason why the interaction Hamiltonian HR, S tilde SR, induces a very weak perturbation only. Now to deal with this equation, let's say this is my equation number 7. To simplify this equation further, let me do the change of the integration variable from, we have the variable as t and t double prime, to variable t dash tau, where tau is the difference of time, t dash minus t double dash. Let us change these variables. Then this integration t plus delta t dt dash t to t dash dt double prime, this would become 0 to delta t d tau t plus tau to t plus delta t dt dash. Let me explain it why I can write it this way. So we have this variables t dash and t double prime, and on the t axis, t dash axis, I am going from the time t to t plus delta t. So we are going from the time t to t plus delta t. Okay, and on the dt dash, I am going from time t to some time t dash. So let's say I am going to this point. So I am going from here and then I am going there. Or I can do this way. If I go by this one, here you see t is equal to t dash. So that means your tau, which is the difference between t and t dash, this is equal to 0 here. So if I take another line here, make another line. So this is say at time t plus tau. Then if I use the variable tau, then I can scan this whole area. Let me say this is O, or say A, B, C, because when I'm changing the integration variable, the area under the curve should remain intact. So I can do one thing, I can go from tau is equal to 0 to up to this point C, where your tau is going to be equal to simply delta t, right? So, and I can go from other variable is t dash here, and t dash I can go from this time t plus tau to t plus delta t, which is what exactly I'm doing here. And then I'm varying tau. Now I'm varying tau from tau is equal to 0 to tau is equal to delta t. And this is the reason I can write this equation. As the correlation time tau c between the reservoir and the system is extremely small compared to delta t, so this is very small compared to delta t, so we can take delta t tends to infinity. In that case, the integration, this integration, double integration t to t plus delta t dt dash integration
t to t dash dt double dash would be equal to, in the new variable tau and t dash, tau, as you have seen, that it goes from 0 to delta t, but now delta t tends to infinity, so I'll put it infinity here, then d tau, and this here I have t to t dash, not t dash, it would be t plus delta t dt dash. Okay, so with this I can rewrite this expression for the system state, system density operator rho tilde delta rho tilde t is equal to minus 1 by h bar square integration 0 to infinity d tau, then integration t to t plus delta t dt dash trace over the reservoir, and here I have this h tilde sr t dash and this commutation h tilde sr t double dash, which is now t dash minus tau, because you recall that tau is equal to t dash minus t double dash, so that means t double dash is equal to t dash minus tau, right? So using this, then we have also rho sr, which we are writing as rho tilde t with the direct product rho tilde r. So this is what we are having. At this stage, we make the assumption that the interaction Hamiltonian HR, this I am writing now in the Schrodinger picture. This in the Schrodinger picture, this interaction Hamiltonian between the system and reservoir can be written as a sum of the product of the system operator and the reservoir operator. So I have this, I can write it now h bar s alpha r alpha with the understanding that the repeated indices imply summation. Now with this, let us have a look at the integrand of this equation. Say this is my equation number 8. Now we are going to look at this particular integrand bit carefully. I hope you have understood the mathematics or the algebra so far clearly. Now let me take you through the steps quickly towards the derivation of the quantum master equation. So as a first step, as we are looking into the expression, the integrand expression, now here in the integrand expression we have the system reservoir Hamiltonian is there at time t dash and t dash minus tau, and these two terms we can write as a sum of the product of the system operator and the reservoir operator. Now putting this expression here, these two expressions if we put here and expand it, then this is the one that we are going to get. Now here this is the commutation relation, and this bracket if I expand it, then this is what I get. And similarly in the next line, this whole thing I am now expanding inside the bracket, this is what I get. While writing this expression, I am not writing t dash and t dash minus tau for the ease of writing. Now if I open it up, this is what I get. Okay, this is what I get. Now in the next step, I am going to take the trace over the reservoir. So all the terms belonging to the reservoir I collect and then take the trace, and in total we are going to get 4 terms. So this is first term, this is the second term, this is the third term, and this is the fourth term. To make it simplify further, now let me write down the time explicitly. For example, let us look at this expression here, and we can now define a function. Let me explain first. So I have here trace over the reservoir elements. So r alpha at time t dash and r beta at time t dash minus tau, rho r, this is nothing but, as you can see, this is nothing but the expectation value of the product of the two reservoir operators at different time in the reservoir basis. Okay, this is the expectation value of the two operators, reservoir operators, taken at time t dash and t dash minus tau, and this is what I get. And this also further I can write if I just put t dash is equal to tau, and then r tilde beta, it would be 0 here, r tilde beta of 0, and this I define as the function z alpha beta tau. Okay, now let me look at the things term by term. For example, if I look at the first term, then as you can see, this is what I have here. Now here I am putting t dash is equal to 0, and this is what I get, and this expression I can write it in this form. So let me say this is my equation 1. Now next term I am going to look at is the this is s beta. This is what I am looking is that term number 3. So if I look at the term number 3, okay, this is term number 3 I am looking. Again here you see I am putting t dash is equal to 0 here, and then here this is the expectation value of the reservoir operators at one at time minus tau and other at time 0. This, because this is at 0 and this I can take it this side and I can take it this side, it's not going to make any difference. But what I am doing, I am now shifting the time, and then I get r alpha tau and r beta 0. Okay, and then this is nothing but my function z alpha beta at time t, at time tau. And then I am looking at the fourth term. If I look at the fourth term, again if I put t dash is equal to 0, so this is what I get, s tilde beta at minus tau, s tilde alpha at time 0, and this is the expectation value on the reservoir basis. But this now I defined as a function z beta alpha. You see the notation here, I am now writing is at z beta alpha at time minus tau. So this is my term number 4, and then I have this term number 2. Okay, I think yeah, this is term number 2. In term number 2, again I am putting t dash is equal to 0, and this is what I get, and finally I get this expression. Now this, all these expressions I put in the expression, and then finally this is going to give me the intriguing expression. This is what actually we wanted to simplify. This expression finally we obtain as this. Okay, now the change in the system quantum state, which is given by delta of rho tilde t. Now this is the integrand we had, and this integrand we have finally evaluated, and we are putting it the whole expression. Then change in the system quantum state is going to be given by this particular expression. Now let us make some further approximation. We are going to take the system operator in the interaction picture as this one. So s tilde alpha. Actually we are now going from the interaction picture to the Schrodinger picture, and here in the interaction picture or the representation, the system operator, we are going to write it in this particular form, s alpha e to the power I omega alpha t. Similarly for s tilde beta, which is a function of t dash minus tau, that we are going to write in this particular form. This we are going to justify by giving some example perhaps in the problem solving session later on. And using this form of the system operator in the interaction picture, I am going to put this expression here for our this expression representing, giving the change of the density operator for the system in the interaction picture. I am going to put s beta, s tilde beta this form here, and s tilde alpha here, and so on. Then if I simplify it, then this is the expression that we are going to get. And as you can see, because of the substitution, we are going to have terms like e to the power I omega alpha t dash, e to the power I omega beta t dash minus tau. Okay, Now this expression we can make simplify further if we just define these three terms. First of all, if I define a term I omega alpha plus omega beta like this, and then z alpha beta plus and z alpha beta minus, then this expression here can be made simplified, and this is what we are going to get by putting these three terms. And now let us look at this particular term carefully. First of all, let me note about the this term I omega alpha plus beta. As you can see, this term I omega alpha plus beta, this one here, this term is highly oscillating, and in the fast dynamics, as we know, fast dynamics of the system and the reservoir, this interaction between the system reservoir, which results in the correlation between them, is very short. And because this is very short, that means it oscillates very highly. If you take the time average of this is going to give me 0 if omega alpha is not equal to minus omega beta. That means basically if omega alpha plus omega beta is not equal to 0, then this term will oscillate very highly, and then if we take the time average, this is going to give me 0. But if omega alpha plus omega beta is equal to 0, then it is going to give me simply delta t if omega alpha plus omega beta is equal to 0. So we can now write, using this information, this integral I of omega alpha plus beta in this particular form. We can use basically the Kronecker delta notation here, because as you know, the Kronecker delta omega alpha minus omega beta simply means that this is equal to 1 if omega alpha is equal to minus omega beta, which means that if omega alpha plus omega beta is equal to 0, and this is equal to 0, this Kronecker delta, if omega alpha is not equal to minus omega beta. Okay, so using this information, we can now write the change in the density operator for the quantum system state in this form, I omega alpha plus beta. I am now just putting this form, delta t Kronecker delta omega alpha minus omega beta. And if I take this delta t to the other side, then I can write how this density operator, change in the density operator with respect to time, I can write this expression. Then in the limit of small delta t, I can write this as rate of change of, in the differential form, rate of change of the density operator for the system. This is what I can write. So then I got the evolution equation for the density matrix for the system operator in the interaction picture in this particular form. Now we actually want to go out of this interaction picture. To do that, I can now write my density operator for the system in the interaction picture is associated with the density operator for the Schrodinger picture by this. I am not writing rho s all the time, just to understand that whenever I am writing rho without tilde, that means the density operator in the Schrodinger picture. And from here we can get this evolution equation for the system density operator in the Schrodinger picture. And delta rho tilde delta t already we have worked out in this expression, so we just put it here, and then finally we get this very important equation which gives us the evolution of the density, system density operator in the Schrodinger picture. Now use the fact that the system reservoir Hamiltonian should always be Hermitian, and therefore we need to ensure the hermitativity. To do that, we have to add this Hermitian conjugate term. If you remember, originally we have taken H SR is equal to H bar S alpha R alpha. Now to ensure the hermitativity, we need to add this Hermitian conjugate term. And in equation number A, that means that we should have S alpha is equal to S beta Dagger, and moreover now we are going to utilize the property of the Kronecker delta, and if we use the property of the Kronecker delta, then instead of this is double summation, as you know, we are going to have a single summation, and we can just have to retain only one of the indices only. So retaining the indices in this alpha, we can now write the evolution equation for the system density operator in this particular form. And also now you note that earlier this term z plus alpha beta and z minus alpha beta will now redefining as z alpha plus and z alpha minus, and z alpha minus is actually the complex conjugate of z alpha plus. It's a complex quantity. Now if we separate out the real and the imaginary parts of the integral, then we can rewrite this expression for the evolution equation for the density operator, system density operator, in this particular form. And now you see it is significantly simplified. Now there are three terms on the right hand side of this equation. The last term, if you look at carefully, it has the form of Hamiltonian evolution. Now if we define a effective Hamiltonian which is resulting due to the reservoir interaction, system reservoir interaction, and it effectively actually results in shifts of energy level of the system only. And using this we can obtain the final form of our evolution equation for the density operator, system density operator, and this is the so-called quantum master equation. Here this capital L, italicized capital L, is the so-called Lindblad super operator. It is said so because as you can see it operates on the density operator rho, and these gamma alphas here represents dissipation or diffusion coupling coefficients, which results due to the interaction of the reservoir with the system. So we have derived the quantum master equation, and this form is known as the Born-Markov Lindblad master equation, and also it is known as the Lindblad form of the master equation in the Born-Markov approximation. For derivation of this Lindblad master equation, I have taken the help of this particular notes by Quantum and Atom Optics by D.A. Steck, and also you can actually look at some other sources such as Quantum Optics by G.S. Agarwal and Quantum Optics by G. Milburn.
Let me stop here for today. In this lecture, we have derived the so-called quantum master equation or the Lindblad master equation. I admit that the derivation is quite involved. However, as I already told you in the beginning, that this lecture is not going to be part of your examination. But however, if you know the derivation or follow the derivation, it will help you later on if you actually try to involve yourself in research. In the next lecture, we are going to see how this quantum Lindblad master equation can be applied to various systems. So see you in the next lecture. Thank you so much.